All right, it seems to be recording, so hopefully I won't screw it up. So I just posted, by the way, a short document on Canvas maybe about an hour ago with a few tips about the various sections from Marian and how to correlate them with my lecture notes and what to kind of get out of the sections. So I'm not going to repeat that now. What I want to do is to first ask if there's questions for me, and then I'm going to go over some of the practice problems that are part of the homework now. So questions? All quiet on the Western Front, so let's attack the Eastern Front then. Something to mix up metaphors really, really bad. By the way, that is a devastating book. If you've not read it, All Quiet on the Western Front, it's about war. How can it be not devastating? But all right. So in class, let me close the door. In class, I got you started on some of the practice problems, right? So what I want to do is just mention a few things about 2D. Then I'm going to essentially set up 3 and set up that last one for production. The problems from Varian are particularly simple. So I'm not going to say too much about it. I gave you a hint about 18.2. That is, you should use the constant returns to scale of the production there. How should you use it? Well, with constant returns to scale in competitive equilibrium, what is the profit in equilibrium? 0. Economic profit of 0. So that means that you have an easy job with a budget constraint of whoever owns shares in that firm, because the profit that you're going to be adding to the budget on the income side is 0. That is not true of the practice problem, the last one. So that's why I want to kind of work through at least the process of getting there. At the end, it gets into some somewhat tedious math, so I'm not going to do that here. So 2D, yeah. Idea here is as follows. We have 2 Leontief utility functions. Let's start with the endowments. This is 2, 1, 0, 1/2 would be handy. All right, so we have this situation. Person A has endowment 2, 0, and person B 0, 1. So this is 1. So the endowment point is right here. Since in this I took it from the source, I took it and modified it. It was omega for the endowment rather than E as in my notes. Sorry about that. I'm going to keep that notation. And we have UA is the min of, let's see, which the 2x1a, x2a, and for person B, min x1b, x2b. So they're pretty much the same except for that coefficient 2 here. Okay? So already we know how to draw UBs in difference curves. So starting from here, we know that the indifference curves will have their corners along the 45-degree line from the point of view of this origin, of course, right? So I put the little dotted lines there as a guideline. Now for this one, Where are the corners? Well, just like in this case, right? You find the corners by setting the two things that are inside the min operator equal to each other, right? So I'm going to do that here just to help me. So 2x1a equals x2a. So x2a, well, I mean, I can view it as x2a is 2x1a. So the line, from the point of view of this origin, is a line with slope 2. So it'll help me to discover here 1, right? I didn't draw it really very well at the middle. Let me try to make it somewhat more convincing as being the midpoint. Alright. So the corners of person A's indifference curves, well, angles, will be along that dotted line, right? So then we have the standard question here. Find all the Pareto efficient allocations, highlight the Pareto efficient allocations that are also individually rational. Make everybody at least as well as the endowment. Okay, now given where the endowment is, well, let's just, first of all, take a generic indifference curve of somebody, right? Remember, how am I going to start figuring out where are the Pareto efficient allocations? I'll need to arbitrarily choose somebody's indifference curve and say, okay, this will be the constraint for the other person to maximize. I don't care who I start with, because the process works just as symmetrically, right? So let me choose, oh, why not? Let me choose this indifference curve for person A. Again, I put a little arrow and pointing in the direction where the person gets happier. And the point of that is to remind ourselves this is an indifference curve of person A. Okay? Now then, the question is, I'm going to make red indifference curves for person B, and then we will mess around with green for the Pareto set and others. So, from the point of view of person B, they're trying to push their indifference curve in that direction, right? And they're going to have to respect this line as the constraint. So, for example, if I consider this indifference curve of person B, that is not the best that person B can do, given that person A has to be at least as happy as at this solid blank indifference curve. So therefore, I'm going to keep pushing down UB until I'm about to leave the feasible set that this constraint creates. So as you will probably find completely convincing, I hope so anyway, where I stop will be this indifference curve, right? Where, despite my best efforts, I made it wavy, but you know, it's supposed to be a straight line there. All right, so what did I find here? The interval from here to there and all the points in between contains points that are Pareto efficient, right? And just to double check that what I said earlier is still correct, if I started with a red solid indifference curve of person B, and I pushed the black one as much high as it will go, I would end up exactly with the same tangency interval, right? So once you recognize that that's the story, then it ought to be fairly clear what the set of Pareto efficient allocations is, right? It's going to be this trapezoid, all of it, all the points in between, including this segment and that segment on the edge, on the boundary of the Edgeworth-Pauli box. So everything here and these points, that is the set of Pareto efficient allocations, okay? And it goes all the way down, by the way, right? The particular black and red indifference curves I chose are just one example. As you can see, I could have chosen the black one down below or higher up. And in fact, you can convince yourself fairly easily, I hope, that even for this segment over here, that is still the case, right? Like if I had chosen this indifference curve of person A, then that's pretty severe as a constraint for person B. But still, the tangency would happen in that overlapping, that line segment that you have the overlapping parts of the indifference curves. So that is, okay, so all this green indicates the set of Pareto efficient allocations. Now, how about allocations that make everybody at least as well off as the endowment? So for those, I recognize in this particular problem, here's my endowment. So from the point of view of person B, I need to be in that direction, right? Because what is the indifference curve that passes through this point? And let's see, actually. For person 1, person A, that's very simple. The axis passes through that. So from the point of view of person A, I need to be anywhere in the box. And he still is just as well off as, or better off than at the endowment. Now how about person B? Well, that's the indifference curve. So how many allocations? The entire box makes everybody at least as well off. In this case, the lens, so to speak, is as big as possible from the endowment. Okay? Question?
Is that typical of Leontief?
Yeah, Leontief, well, what? The fact that the set of Pareto efficient allocations is two-dimensional rather than one is typical.
Okay.
Right?
Mm-hmm.
And let's see what else. In the indifference, the individual rational allocations, this happened to be, because of where the endowment is,
okay,
to be as big as possible. But, you know, feel free to move the endowment somewhere else in the very same example and redo it.
okay.
Right?
Yeah.
So, for example, well, what if the endowment were here? Okay, so this is not the problem as set, but let's put the endowment here and see what happens, right? What is the set of Pareto? Well, the set of Pareto efficient allocations, it doesn't matter, right? Remember, ownership, private institutions, private property, prices, ownership has nothing to do with Pareto efficient allocations, right? So nothing changes in terms of the green of the Pareto efficient points, okay? But now that we know that the point of ownership is here, then what are the indifference curves? Well, we actually have them, that's why I put it there. So for person B, we need to be on this indifference curve on this side of it, and for the other over there. So suddenly, we have a thin individually rational / Pareto efficient set.
Okay.
Okay? So basically all of these 2A, B, C, D are problems to make you think about this in terms of maximization and apply the definitions directly rather than to just automatically jump to looking for something tangencies and setting derivative ratios equal to 0 to each other. Okay? Because the logic, I think, is much more clear when you have to do it this way. Any questions on this? All right, so let's do problem 3. It's actually kind of easy, but I'll at least let you start it. Okay, so 3 is a very symmetric problem, right? Where we have Cobb-Douglas for both with equal exponents. And the only things that are not equal are the endowments of the two individuals. One person A has endowment 1 of the first good and 5 of the second, and for the other we flip it, it's 5 and 1. Okay? So, all right. So you look at it and you realize from the point of view of the markets, what is the total amount of good 1? 6. What is the total amount of good 2? 6. The two individuals have Cobb-Douglas with equal exponents. So each one will spend exactly 1/2 of their income, whatever their income is, on good 1 and the other half on good 2, right? So at this point, you don't even need to do the Lagrangian. I mean, Cobb-Douglas, it's okay to say, I know you split the income according to the income shares that the exponents of the Cobb-Douglas indicate, and so when the exponents are equal, then you split it half and half, right? Not the amount you buy, but the amount you spend on each good has to be following that rule, okay? So that speeds you up to the calculation of the demands of the two individuals, right? But we haven't even gone to that yet. It's just, I'm just getting recognizing all the things that can help me here. So I recognize this. But before that, the first sub-question, A, says Pareto efficient allocations. Find them. Is there anything asymmetric here? No. The problem is completely symmetric. From the point of view of Pareto efficiency, who cares if one has 5 and 1 and the other has 1 and 5, right? So you kind of expect that the Pareto efficient allocations, when you draw them in the box, will go from one origin to the other, in fact, on a straight line. So expect that, and you do the calculations, and if something turns out wrong, then really look at your calculations again. Something went wrong, right? So, okay, so for part A, you can do it as follows. Maximize by choice of x1a and x2a the product of the two, which is the utility of person A, and you're going to have as a constraint that person B is going to be at some arbitrarily selected utility level, yeah? So let's say x1b, x2b is greater than or equal to some utility level, which I will simply write ub bar. I need some notation to remind me it's an arbitrary constant. Okay? So in all of those problems, when I see strictly increasing utility, then I know that even though the constraint is weak inequality, at the end it's going to be equal. All right? The Lagrangian here is going to be this, right? And from this, you should be able to very quickly prove that the two marginal rates of substitution have to be equal. Do it. I'm not going to do all of these little details. This is easy. Once you have that, then you will have, so I'm not doing this step, but what would it mean here to say this? It means that x2a over x1a equals x2b over x1b, right? So it appears that we have 4 unknowns here, but we don't, because x2b is the total amount available of good b, good 2, which is 6, minus x2a, and down here 6 minus x1a, right? So notice I have no prices here whatsoever. And the only use I made of the endowment is by first aggregating it for its commodity across the two people, right? So, in fact, I'm being so far completely agnostic about who owns what part of the endowment. For this, it doesn't matter. Okay, so now I can take this and set it equal to that. And guess what I'm going to get? That x1a and x2a have to be equal to each other. You can do the cross multiplication. It's pretty obvious, however. All right, so x1a and x2a have to be equal to each other, which means x1b and x2b have to be equal to each other. So that pretty much settles. I don't know the exact numbers, and I cannot know the exact numbers unless you give me what is this number. But that's irrelevant. By now, if I make my box of dimension 6 and 6, right? Then I know I'm along the 45-degree line, which, because the box is square, connects the two origins. So here is my set of Pareto efficient allocations, all of it. Okay? It's quite easy, and you should just do it just for the fun of it. To modify this problem slightly, like change one of the total endowments. So don't make it all that symmetric. Or put one utility to have like a 1/3 and 2/3 and leave the other alone. And do it and see how does it look. Okay? Easy exercises, and should such a thing show up on the final, I would not feel that I misled you in any way. Okay? Get some practice on that. This is easy. With Cobb-Douglas, the marginal rates of substitution are so simple. So play with it. Okay. That was part A. Part B, find the individual and the market excess demand functions and find the associated valuation equilibrium prices and allocations. So I'll get you started with that, and again, not finish it. Right, so that was part A. Let's see, part B. I'm going to keep this maximization here, but I'm going to change the constraint, because now I'm going to use it to find the demand function for good 1 and for good 2 that is expressed by person A. For that, I need person A's budget, right? So what I'm doing now is I'm changing the constraints, but I'm still at the moment maximizing this utility function. Then I'm going to do it for person B's, and then I'll put things together and find the excess demand. So, subject 2. So this is part of B. I should have written that here. Okay, so I need notation for prices. Since I have goods 1 and 2, how about P1 and P2? All right? So P1 X1 plus X1A plus P2 times X2A equals, okay, what is the income of person A? Well, they have 1 unit of good 1. Yeah, so P1 times 1 plus P2 times 5 is person A's value of the endowment, right? Okay. The person is going to split their expenses so that half of this is spent on X1 and half is spent on X2. All right? Do the same for the other person, right? Now you have the demand for good 1 from person A and from person B. Then you have the demand for good 2 from person A and from person B. And you know that the supply for good 1 is 6, and the the supply for good 2 is 6. So writing down the excess demand for each good is easy once you've done this, right? It hardly requires any calculations, really. So far, so good? So now you have your excess demands. If you solve 1 equal to 0, then you're good, right? Because we really have 2 equilibrium conditions, and we know that if one works, the other follows automatically, right? Laurent's law. Okay, so that is all I'm going to say for part B. Part C is slightly more interesting. And I'll do a little picture first. So this, again, 6. That's the dimensions of this box. And, okay, what does it say? Show directly that every interior Pareto efficient allocation in this economy is a price equilibrium with transfers by finding the associated prices and the transfers. Okay? But incidentally, in part B, I forgot to mention at the end of the day, you have 2 prices floating around. So, but we know only the relative price matters. So feel free to set, for example, P1 equal to 1 and normalize it this way. If you feel like setting P1 plus P2 equal to 1, I don't care. But you know, some sort of price normalization is always done. It would be somewhat more interesting in the last problem where we will have 3 commodities to price. Still, it would be obvious there how to normalize for the most convenient mathematics. So, now, we already know that the set of Pareto efficient allocations is this diagonal of the box, and specifically we are required to consider points in the interior. So I am not going to try to support the origins because they're not in the interior. Okay? All right. So, okay, where is the endowment, by the way? If I have 5 over here, then the endowment is over there, right? Okay, so let's take an arbitrary point, let's say here. It's arbitrary in D. Choose wherever you want to put it. Now, where did I choose it? In the set of Pareto efficient allocations. What do I know about the indifference curves that pass through it? They're going to be tangent to each other in this case, right? And in fact, they will have what slope? A number. Yes? -1. Total symmetry, right? x1a and x2a are equal to each other. The margin rate of substitution is x2a divided by x1a. So we have 1. Put a minus in front because we're talking about the slope. So there you go. Okay? All right.
It's been a week.
Okay. I understand that. So I know that my support line for this allocation has to be like so. Slope of -1. So the idea being that the 2 indifference curves are just like that, tangent at that point. All right? Oh, well, what about those transfers? And well, first of all, the welfare theorems. Do they apply? Yes. The second welfare theorem in particular applies here because everybody has positive income. C 17.3 invariant for that. The problem, I mean. And preferences are convex. So what do I know from that? I know that I ought to be able to support this as a price equilibrium with transfers, as I called it in my lecture notes. But it's not a Walrasian equilibrium from this endowment, unless I, by complete accident, chose the midpoint here, right? Where then my support line will go through the endowment. So the whole thing is to adjust for the fact that the support line in general is not going to pass through the endowment. So then you have to ask, okay, all right, what do I do to bring the two individuals to some point, right, in which they perceive their incomes as such as giving them this budget line. So then you have to say, okay, so what is then the transfer? I'll start it for person A. What sort of transfer? Clearly, I'm going to be taking away money from person A, right? Because this line is way below where the endowment is from the point of view of person A. But, I mean, this is because I chose the point here. I would have chosen it there, and it would have been the other way around. Okay, so okay. I will have some amount. This point is arbitrarily chosen, so I better give some notation to indicate just how much is the amount x1a and x2a, which are equal. So how about I call it something like x hat? And x hat is a number that is completely up to me in particular, but it has a restriction, right? It needs to belong to the open interval from 0 to 6, because I said it needs to be in the interior. So positive consumptions for everybody. Okay? All right, so now, if I call TA the transfer to person A, and it can be positive or negative. If it's positive, it's money I give to person A. And if it's negative, it's, well, the other way around. And by the way, TA will be equal to negative TB, right? The money I give to A, I take from B, or if I give it to B, I take it from A. So if I figure it out from the budget constraint of person A, then I'm done. I can immediately see what it is for the other person. Okay? So, right. So I want the budget constraint for person A to look like this. I want it to be P1 x1a plus P2 x2a equals, and it's going to be P1 x hat plus P2 x hat, right? So I want the person A to be able to afford to buy that point. That's what it means. I brought them down to that budget line, right? Now, of course, that means P1 plus P2 x hat. X hat is the same. So this is what I want the income to be for person A. So I can also write what the income was with the original endowment. P1 times 1 plus P2 times 5 plus the transfer. And I set these two amounts equal. Find the transfer. Again, I could normalize P1 to P1, for example. And in fact, if I do that, because of the entire symmetry, I know P2 is going to be 1 as well, right? So this is how you would find the transfers. Any questions? Okay. So that pretty much does this problem, right? So now let's move to the one with production. Any questions before I erase? You sure? All right, very good. So problem, let's call it 4. It's 2-1 here. Well, 2-1. So we have 3 commodities here. So 3 commodities. We have, let's see, labor or leisure, right? We have commodity X1 and commodity X2, the 2 outputs. There are 2 firms, and one makes the commodity 1, the other makes commodity 2. And the utility functions are only defined in terms of the outputs. So the individuals here, they have the endowment, which I called labor, but it doesn't enter their utility function. So it's simpler than the full-blown model in which the leisure also affects their utility level, right? So that's a little thing to make it easier. Because the whole point of this is to kind of really work with budgets that include profits that are not 0. And so see what is the sequence of operations you have to do. Plus, one utility function is Cobb-Douglas and the other isn't. So Cobb-Douglas for person A and perfect substitutes for person B, right? So that already should make you suspect that person A might be wanting an interior location for their consumption, but for person B, you can't avoid looking at the boundary consumptions. It will all depend on the price ratio. So let's put notation for the prices, and then I'll write down the production functions and start. So for the prices, I propose this notation. PL, P1, P2. Okay? By the way, L, an endowment L bar of 25 is owned by person A, right? And person B has no endowment of L, but owns the firms. So in some sense, we have the proletarians, where person A is a proletarian who has to work, and person B is the dirty capitalist that owns both the firms 100%. Well, clean capitalist, whatever, but owns both the firms. Okay? So, you know, the theta 1A will be 0, right? Theta 2A is 0. Theta 1B is 1. And theta 2B is 1. It's kind of an extreme case, but again, it makes the math, you'll see, this is a bit more tedious than the others. So you want to kind of simplify as much as possible, so you just focus on the process here. All right, so have I specified everything? Not quite. I still need the production functions. So for good 1, the output, good 1 is going to be square root of 2L1. For good 2, square root of 2L2. And y1 plus, I'm sorry, feasibility condition is L1 plus L2 must equal 25. Because that's it, right? There's no other amount. That's the only source of input is the endowment of person A. So now I think I have pretty much everything, right? Okay. Let's set this equal to 1. I have 3 prices. I can normalize by setting 1 to 1, and I could, if I think of this as the wage, then okay, then I normalize everything in terms of purchasing power of the worker. All right. Okay, how do I go about it? Let's see, what does it exactly ask me to do? Find the origin equilibrium, and then is this unique? All right. So, start with the producers. Why? Look at these production functions. They have decreasing returns to scale. Each one of them is a strictly concave function of the input, right? Square root concave function. So you know the equilibrium profit will actually be positive for both firms. So therefore, find the profit, the optimal profit first. Then you're going to put it in the budget constraint of person B, who is the one who actually receives the profits. And then you can finally do demands. So profits first. So profit max. So there's 2 firms, they're pretty much practically identical, right? So let's do one and you can do the other. So what is the profit of firm 1? By 1, we have the price 1, which is the price of the output it produces, times how much output it produces, which we are told is equal to this, right? Minus the price PL times the amount of input that it uses, but we call this 1. Right? Okay, I want to maximize that by choice of L1. So I'm going to maximize this with respect to L1, the only thing that the firm gets to choose. There's only one input. So the first order condition is going to be, and now you see why the 2 isn't there, because the square root is going to give you 1/2, and well, let's see. So the derivative of this is going to be 1/2 times 1 over square root of 2L1 times 2, which is the derivative of the inner function. And then minus, minus 1. Right? So I set this equal to 0. This cancels with that. And what do I see? That L1 square root of 2L1 has to equal 1. Right? So 4L1 square is 1. And so L1 square is 1/4. L1 is 1/2. Did I make a mistake here? So this actually, let's put this here that way. Okay. So far so good? Am I missing anything? Of course I am. You didn't catch me. Where's the price P1? Ha ha ha. Right. Now let's check. Yes, right? So therefore, L1 is B1 half over 2. Is that right? Nah, no, it's not. It's just terrible today. There, I ought to be correct. Is it? Okay. You see, square root of 2 on the denominator. Right?
Yeah.
Yeah? And there is also a negative root, but who cares?
Yeah.
Right? Okay? So you?
I think the error don't have a square.
Uh-huh. Thank you. Okay.
Sometimes. I never see it. Algebra is my biggest enemy.
This is the one case that I did this on purpose. Usually in the classroom, it's an accident, and I admit it. Now, it's not an accident. And I kind of even provided a little hint when I suddenly changed this to less than or equal to. Because it looked like it was getting a very small usage of L, right? And then suddenly, how is that possible? Why is the price of output not there? But you were all looking at me thinking, oh, he's not going to try to trick us. Of course he is, he. Okay. All right, okay. Now, let's assume this is correct. So double check everything. But that tells me what? That tells me that I have L star 1, the optimal usage of the input for firm 1. Do it again for firm 2, and come on. For that one, you will get P2 squared over 2, right? Nothing is different except the subscripts. But in this one, don't be tempted to think that one of the P1 or P2 can be 1, because we have 3 prices and we already set 1 to 1. So P1 and P2 need to stay in your notation. Okay? All right. So what is then the optimal output of 1, Y1, for firm 1? It is square root 2 times L1 star, whatever that is, put it in here. Actually, let's do it. So it's square root of 2 times P1 squared divided by 2. And look at that. So P1, all right? And similarly for the other one. So the supply curves are about as simple as you would wish them to be. But we double check. Is it a reasonable thing for the supply curve to be an increasing function with slope 1? Of course it should be an increasing function. Okay, so far so good, at least in terms of not getting any nasty surprises. If this turned out to have a negative slope, we would say, okay, what did I do? Okay? All right. Fine. Finally, what is the optimal profit? For firm 1, all you have to do is take the expression for the profit and substitute what you found for the L input, right? So what did we find? We find L1 P1 squared over 2. So I'm going to, and actually I know the output. I already calculated that this should be P1. So it is P1 times P1 minus, that's it, times, minus, the L1 is P1 square over 2. So hey, voila, P1 square over 2 is the profit of firm 1. Identical profit for firm 2. So the total income of person B is going to be P1 squared over 2 plus P2 squared over 2. Right? Because the P2 pi 2 squared, pi 2 star is going to be P2 squared over 2. So now you know how to write the budget for person 2. For person 1, it's quite simple because they only get income equal to 1 times 25, right? Because they only own the 25 units of the input. So now you have a problem to maximize the utility of person 1 where the value of their expenses equals 25, and you maximize the utility of person B where the value of their expenses equals this, and you will have from that demand functions from both of them. And there you will have to make cases for person B. What if P1 is less than P2 and then they only buy good 1? What if the other way around? And what if P1 and P2 are equal? So that's the tediousness. Not that it's particularly difficult math, but you know. So for person B, you'll have to consider that, set up the maximization problem. And now for person 1, it's pretty easy. It's a Cobb-Douglas, right? So in fact, you can kind of see already that P1 times X1A is going to be 25 over 2. And P2 times X2A is going to be 25 over 2, right? So the demands for person A are immediate. The demands for person B break down depending on where you think the price is P1 less than P2, P1 bigger than P2, or they happen to be equal. So now we have a way of writing down all the demands, and we have the supplies. So you can now write excess demands for all the goods. What is the excess demand for good 1? Well, the demand you calculate by adding the demands of person A and B minus a supply, which you have here. For the other good, add the demands for person A and B and subtract the supply. And there's one more. To L1 minus plus L2 minus 25 is the excess demand for the input. All of these three have to be met with equality. But again, you know from Alvarez's law that if 2 of them are satisfied as equalities, the third one will automatically be, right? So then your conditions for equilibrium will be excess demand for good 1 is 0, and let's say excess demand for good 2 is 0. But you have it in 3 different cases, right? So take the case where P1 is less than P2. Write the excess demands for the 2 goods equal to 0. Solve it for P1, P2. Now, is your answer going to show P1 less than P2? Then it's an equilibrium. But you've assumed that P1 is less than P2, so it better come out after you do the calculation of the prices, yes? For the other case, exactly the same, but you're going to assume P1 is bigger than P2. And the case P1 equals P2 is, in terms of math, the simplest of the equations. But yeah, and so you go ahead and you try to calculate what is the common price P1, P2 that will give the 2 excess demands equal to 0. And then you have to decide for yourself, did I find 3 equilibria or did I find just 1? Incidentally, again, intuition, without having done the calculations, I know that the P1 equal P2 case will be an equilibrium because there is no asymmetry here. Everything is completely symmetric, right? Symmetric exponents, equal exponents here, symmetric coefficients here, equal production functions. There is nothing asymmetric in this. So I know that the case P1 equals P2 will work out and it will be in equilibrium. And if I somehow don't manage that, then something went wrong in my calculations. For the other cases, I will leave it up to you. Can you get an equilibrium with P1 less than P2? And can you get an equilibrium with P2 less than P1? Okay. Any questions? Okay. So I will leave you to it.